We're going to look at some methods of solving equations using complex numbers in this video. This first example, there are two ways of doing it. One way that is kind of more obvious than the other ones, and one that is less obvious but is a foolproof method that will work no matter what your equation is. The obvious way of solving this to start off with, and I'm going to do this for both methods, is to first minus the 3 and add the 4i across to the right hand side. I, z. Minus 3 across gives me 2, adding the 4i across gives me 10i. Then, obvious thing to do is to divide through by 1 plus I. So I've got 2 plus 10i over 1 plus I. I can't leave my answer like this. I do need the i's to be all on the top. So I'm going to times through by the conjugate of the denominator, so 1 minus I. Expanding at the top gives you 2 minus 2i plus 10i minus 10i squared. And expanding at the bottom gives you 1 minus I plus I minus I squared. On the bottom, your i's should cancel out. Remember, I squared is minus 1. So on the top, collect up my real bits. I've got 2. Minus 10i squared becomes plus 10 because I squared is minus 1. So that's 12. And then I've got minus 2i plus 10i. Using plus 8i. 1 minus I squared, well, I squared is minus 1, so that's 1 plus 1 is 2. And then I'm going to cancel this and write it as 6 plus 4i. This is the obvious way of solving this equation. However, when you start getting equations involving conjugates and things like that, this method will not work to get z on its own. Instead, we need a different approach. So the different approach that we're going to take is to start off by writing z as a plus bi. We don't usually write this, but a and b are real numbers in this case. They can't be imaginary. I'm going to substitute this in, and I'm going to start off the same way as we did in the last one. So I'm going to start off from 1 plus I times z is 2 plus 10i, but this time I'm going to then substitute in a plus bi instead of z. If I expand out the left-hand side, I get a plus bi plus ai plus bi squared. And I can collect up the real and imaginary parts of this. So I squared is minus 1. So real parts, I've got a minus b. And from my imaginary bits, the bits with I on, I've got b plus a. Now what I'm going to do next is just like equating coefficients, except instead I'm going to equate the real and imaginary parts. So whatever's real on the left-hand side, which is a minus b, must be equal to whatever's real on the right-hand side, which is 2. And whatever's imaginary on the left-hand side, which is b plus a, must be equal to 10, the imaginary parts on the right-hand side. Don't need to include I for those ones, just like you wouldn't include x if you were equating x coefficients. You can solve these by hand or solve them in your calculator. So if I add these equations together, I'll get 2a equals 12 and a equals 6. And if I put a is 6 into either of these, I can work out that b is 4. That tells me that z is 6 plus 4i, exactly the same as we got from the first method. But we can use this method to solve example 2. So in example 2, the difference is we've got a z star in there. But remember that z conjugate. So I can't solve this with method 1. I can't rearrange to make z the subject because I've got z and z star. There's no way of writing one in the way of the other. But if I let z equals a plus bi, z star, remember, is the conjugate, which is a minus bi. So I can substitute these in. 1 plus 5i minus 2a minus bi. I'm going to expand out these brackets on the left-hand side. So I've got a plus bi plus 5ai plus 5bi squared minus 2a plus 2bi, and that's equal to 3 plus 7i. Collecting up my real parts on the left-hand side. So real bits I've got are A, minus 2a, and I've also got 5bi squared. Remember, I squared is minus 1. Putting that together, so a minus 2a gives me minus a, and I squared is minus 1, so that's minus 5b. That's equal to the real part on the right-hand side, which is 3. Collecting up my imaginary parts, I've got bi, 5ai, and 2bi. That gives me 5a plus 3b on the left-hand side. On the right-hand side, that's equal to 7. Again, you can solve these on your calculator, or you could times equation 1 by 5 and solve it that way. So if we do, so we get, if we solve it that way, I get b is minus 1, and I get a is 2, which tells me z is 2 minus I. There's a question for you, you try. So pause the video, have a go at that, and then I'll reveal the answer for you to have a check. Next, we're going to have a look at something which isn't strictly on the specification, but you could get asked to do. So this is asking you to solve z squared equals minus 3 plus 4i. This is equivalent to finding the square root of a complex number. Technically plus or minus. Okay, which you can do on your calculator, but we're going to do this by hand. We're going to start exactly the same way as we've done the previous examples. So z is a plus bi. Substitute that into the left-hand side. It's equal to minus 3 plus 4i. Expanding this out gives me a squared plus 2abi plus b squared I squared. And that's equal to minus 3 plus 4i. And if I collect up my real and imaginary parts, the I squared is minus 1, so I get a squared minus b squared. And my imaginary parts are 2ab. Equating those gives me two equations, so a squared minus b squared is minus 3, and I get 2ab equals 4. Fortunately, these aren't linear, so you can't solve them in the calculator. So we're going to solve these by hand instead. Now, if I take equation 2 and simplify that, so I can cancel 2 off both sides and divide through by a. So I'll get b is 2 over a. I can sub that in, which gives me a squared minus 2 over a equals minus 3. And I'm going to times through by a squared in this case, so I get a to the 4 minus 4 equals minus 3a squared, which will give me a quadratic in a squared. You can solve this on your calculator or you can solve it by hand. And this will give me two values for a. Either I get, sorry, this is squared. I get a squared is minus 4, or I get a squared is 1. Now we know that a squared equals minus 4 has solutions now. It has imaginary solutions. But in one of the previous examples, we said that a and b have to be real numbers. And so a squared equals minus 4 doesn't have real solutions. So we're going to discount that. Instead, we're going to just have a's plus or minus 1. If I take that and substitute it in to work out b then, so when a is 1, you get b is 2, and when a is minus 1, you get b is minus 2. That tells you the solutions to these are the square roots of this complex number are 1 plus 2i, or minus 1 minus 2i. Pause the video again, have a go at this question for you, and again, I'll reveal the answer in a few seconds. The remainder of this pack is concerned with the relationships between the coefficients of a quadratic equation, which in this case are a, b, c, and the roots of a quadratic equation, which we're calling alpha and beta. We're going to start off by looking at quadratics, but moving on to looking at cubics and quartics as well. I'm going to show where these results come from, but it's not essential that you learn this proof. All you need to do is learn the results of these. Let's start off with a quadratic that has roots alpha and beta. We can write it like this. So I can write it in brackets with x minus alpha and x minus beta. If that's equal to 0, I don't know if there was a number at front of there, so I'm just going to call that in. And all I'm going to do from here is just expand that out. I'll get x squared minus alpha x minus beta x plus alpha beta equals 0. And I'm going to collect up the x terms and expand this out further. So if I factorize out minus x from the middle two terms, I'll get ax squared minus ax alpha plus beta plus a alpha beta equal to 0. I can equate the coefficients of this with the original quadratic. So looking at the x squared terms, they're the same. They're just ax squared. Looking at the x terms, I get that b is minus a alpha plus beta. Now looking at the number term, I get that c is equal to a alpha beta. Dividing both sides through by a or minus a in the case of the first one, I get a result that alpha plus beta equals minus b over a, and I get that alpha beta is c over a from the second. This tells us that it's always true that the sum of the roots, so alpha plus beta, for a quadratic equation is equal to minus b over a from the coefficients. And likewise, the product of the roots, alpha times beta, is always equal to c over a for a quadratic. We often write sum of roots as sigma alpha, always equal to minus b over a. The product of the roots in this case is alpha beta, and that's equal to c over a. Definitely worth learning these. They're not on the formula sheet. This means we can write down results about the roots without actually calculating them themselves. So this first one, we've got a quadratic equation, and we're being asked to write down alpha plus beta. We know alpha plus beta is equal to minus b over a. In this case, b is minus 6 and a is 3. So get minus 6 over 3, which gives me 2. For the sum of the roots, alpha beta is always equal to c over a, which in this case is 20 over 3. So I can write those down without working out alpha and beta. Have a go at the U, try it, and I'll reveal the answer in a second. Now, the next example is a couple of approaches you could take. So find a quadratic equation with roots minus 4 and 5 over 2. Obviously, you could put these into brackets and expand them out, and that would be fine. But we're going to use a method that practices using our sum and product of roots. Start off with the sum of the roots. So alpha plus beta, that's equal to minus 4 plus 5 over 2. Gives you minus 3 over 2. We know that the sum of the roots is equal to minus b over a. So I'm going to write that equal minus b over a and come back to that later. If we now use the product of the roots, so minus 4 times 5 over 2, minus 10, we know that that's equal to c over a for a quadratic. Here I've got two equations in 3 unknowns. So usually you have 2 equations in 2 unknowns and you can solve them simultaneously to find x and y. Here we've got a free unknown. So we've got one more unknown than equations. It means I'm free to choose one of them to be whatever I want. So I'm going to choose in this case a to be 2 because of this one here. It makes sense for a to be 2 because that's a fraction over 2. If a is 2, I can then work out b. So I'll have minus 3 equals minus b, so b is 3. And if a is 2, I can times it by that 2 and get that c is minus 20. This tells me that the original quadratic with roots minus 4 and 5 over 2 is 2x squared plus 3x minus 20. You could solve that in your calculator as a check if you like. I'll reveal the answer to you. Try in a few seconds if you want to pause the video. We can apply the same approach to equations which have roots which are irrational. So here we've got one that has roots -3 plus or minus root 10. Do the same thing, so adding the roots together. So -3 plus root 10 plus -3 minus root 10. The thirds will cancel and you just get -6. And just like before, this is equal to minus b over a. We do the product of the roots as well, so -3 plus root 10 times -3 minus root 10. If I expand this out, I will get 9 minus 3 root 10 plus 3 root 10 minus 10. Again, the thirds cancel out. I get left with -1, and this time that's equal to c over a. Two equations and three unknowns means that I'm free to choose one of them to be whatever I want. This time I'm going to choose a to be 1. There's no fractions involved, so it's easy to choose a to be 1. That makes b equal to 6, and it makes c equal to -1. So my original equation, which has these roots, must be equal to x squared plus 6x minus 1. Again, attempt that you try, and in a few seconds I'll reveal the answer. Now, all the ones we've looked at so far have had real roots, but obviously we're doing complex numbers. It's possible to get quadratics with complex roots as well. When you've got a negative discriminant, we say there's no real roots, which means there are complex roots. So for this one here, let's find these complex roots using completing the square. Could use the formula as well. Half the x term, square, take it away. That gives you a +1. So if I take that across, equal to -1. I can square root both sides. Don't forget you plus or minus. Root -1, remember, is I, so I can write the roots of this as -1 plus or minus I. Notice here we've got two roots as a conjugate pair. So because the sign is changed on the imaginary part, there's a conjugate pair -1 plus I and -1 minus I. This will always be true for equations that you're going to come across. So any equation with real coefficients, if it's got complex roots, one of them will always be the conjugate of the other. This is true for quadratics, cubics, vortics, and so on. Makes it really easy to write down the second root if you already know one root is complex for a polynomial. Polynomials with complex coefficients are beyond the scope of further maths. They're not too hard, but they're just not on the spec, so you don't need to worry about them. For another question here, asks us to find a quadratic. We're told one root is 3 minus 5i, call that alpha, and very easily, now that I know that complex roots appear in conjugate pairs, I can write down the second root as 3 plus 5i. It then wants us to use this to work out the values of p and q, so obviously you can put this in a bracket and expand it out, but I'm going to use the sum and product of roots method again. So adding my roots up, the i's will cancel and I just get 6, and this is equal to -b over a. And multiply my roots together. And expand this out gives me 9 plus 15i minus 15i minus 25i squared. I squared is -1, so if I add this to 9, I get 34, and i's cancel out. This is equal to c over a. If I choose a equals 1 in this case, I'll work out that b must be -6 and c must be 34. So the original equation was z squared minus 6z plus 34 equals 0. Pause the video, try the U-try, and I'll reveal the answer in a couple of seconds.